41 light years from where you are sitting right now, there is a planet where the ground never cools, where an entire ocean of molten rock stretches permanently across one hemisphere, and the sky above it is not empty. It is breathing. Scientists have studied this world for over 20 years. They thought they understood it. Then the James Webb Space Telescope looked at it again, and every major model built to explain this planet quietly collapsed. Not one prediction held up. Not one. This is the story of 55 Cancri A, what it actually is, why it took the most powerful telescope ever built to finally see it clearly, and what it tells us about the fate of rocky planets orbiting dangerously close to their stars. 55 Cancri E was first discovered in 2004, orbiting a star just barely visible to the naked eye on a clear night, roughly 41 light-years away in the constellation Cancer. From the very beginning, this planet was unusual. It is classified as a super-Earth, larger than our planet but still rocky rather than gaseous, measuring approximately 1.88 times Earth's radius and roughly 8 times Earth's mass. But the detail that stopped scientists in their tracks was its orbital period. This planet completes a full orbit around its star in just 17 hours. Not 17 months, 17 hours. For comparison, Mercury, the innermost planet of our own solar system, takes 88 days to complete a single orbit. On 55 Cancri E, a year passes in less time than most people's work week. Being that close to a star does something extreme to a planet. The same side of 55 Cancri A permanently faces its star, tidally locked, the way our moon always shows the same face to Earth. That dayside is subjected to such relentless radiation and heat that early researchers concluded the surface had to be a global ocean of molten rock, a literal sea of lava stretched across an entire hemisphere forever. For years, the leading theory was simple and severe. This planet had at best a thin, wispy veil of vaporized rock clinging to its surface, not a real atmosphere in any meaningful sense. Just stone boiled directly into gas by the heat of a star it could never escape. Some early density estimates even led astronomers to speculate about a carbon-rich interior compressed into something resembling an enormous diamond. That theory made headlines for years. It also turned out to be almost certainly wrong. Here is where Webb changed everything. Researchers pointed the telescope's instruments at 55 Cancri E and measured something specific: its thermal emission, the heat energy radiating from the planet as infrared light. If the leading theory was correct, if this truly was bare molten rock with no atmosphere redistributing heat, then the dayside temperature should have measured around 4,000 degrees Fahrenheit, approximately 2,200 degrees Celsius. Instead, Webb's MIRI instrument, the mid-infrared instrument, measured a dayside temperature of roughly 2,800 degrees Fahrenheit, around 1,540 degrees Celsius. Still hot enough to melt nearly every rock and metal we know of, but more than 1,000 degrees cooler than the bare rock model predicted. In planetary science, a discrepancy that large is not a rounding error. It is a signal. Something is actively moving heat from the dayside toward the night side, something that should not be there if the surface were truly airless. The research team, led by scientist Renu Hu, concluded that lava flows alone could not account for that kind of heat redistribution. Molten rock can carry some warmth across a planet's surface, but not efficiently enough, not fast enough to explain a temperature gap of more than 1,000 degrees. The far more likely explanation, supported by the data, was a genuine volatile-rich atmosphere, an actual layer of gas wrapped around this planet, actively transporting heat the way a real atmosphere behaves. When the team then analyzed data from Webb's NIRCam instrument, the near-infrared camera, the patterns aligned precisely with that conclusion: a dynamic atmosphere, not a thin chemical ghost, a real moving layer of gas. Then came an even more detailed follow-up. Using Webb to observe 5 separate eclipses of 55 Cancri E passing behind its star, the team compared each set of readings against long-standing models of how rocky exoplanets are expected to behave. What they found did not match the old prediction of a static carbon monoxide and carbon dioxide atmosphere sitting quietly above the surface. Instead, the data pointed to something far more dynamic, an atmosphere composed mostly of carbon monoxide, with smaller amounts of carbon dioxide, and, unexpectedly, a significant abundance of hydrogen. And the differences observed across those 5 separate eclipses were not random noise. They suggested the atmosphere itself is actively changing, shaped by gases escaping from the planet's molten interior in real time. This is not a fixed, stable atmosphere sitting still above the surface. It is an atmosphere directly connected to what is happening inside the planet, constantly being replenished by volcanic outgassing from below. Some researchers have even proposed that this outgassing may be generating temporary clouds that briefly form above the molten surface before dissolving as fresh gas erupts from underneath. Scientists describe this connection using a concept called the planet's redox state, essentially the chemical balance between oxygen and hydrogen deep inside a rocky world's interior. On 55 Cancri E, hydrogen appears to be strongly favored over oxygen in that internal balance. And that imbalance is precisely what is producing the hydrogen-rich atmosphere Webb detected. The researchers noted something profound in their findings. Since the secondary atmospheres of rocky planets are shaped by the composition of their interiors and the outgassing that follows, the atmosphere itself becomes a directly readable signature of what is happening deep inside a world we will never physically visit. Consider what that means. By studying a paper-thin layer of gas floating around a planet 41 light-years away, scientists can begin to read the chemistry of that planet's molten core. Why does this matter beyond one strange and distant world? Because 55 Cancri E is not alone. Lava planets, worlds so close to their stars that their surfaces remain permanently molten, have become one of the most active frontiers in exoplanet research over the past decade. Planets like K2-141b, L98-59d, TOI-561b, HD63433d, and Korot-7b all share the same brutal category, tidally locked, blisteringly hot, orbiting their stars in anywhere from roughly 6 hours to just over a week. Each one is a natural laboratory for understanding something we genuinely cannot recreate on Earth: how a rocky planet's atmosphere behaves when it is being actively cooked and replenished by extreme heat in real time. Earth's own atmosphere formed and evolved across billions of years through processes we can only partially reconstruct from geological evidence. On 55 Cancri E, scientists may be watching an early version of that same fundamental process, atmosphere formation through volcanic outgassing, unfolding right now, in a system we can actually point a telescope toward. This discovery also says something important about how science actually progresses. For years, the dominant model for 55 Cancri E was a bare, airless, rocky world, possibly with a diamond interior. That theory was not careless. It was the best conclusion available, given the instruments and data researchers had at the time. Webb did not simply add a new detail to that picture. It overturned the picture entirely. And that is precisely how good science is supposed to work. A better instrument arrives, better data comes in, and researchers are willing to abandon a theory they have defended for 2 decades the moment the evidence stops supporting it. No one hid the data. No one resisted the conclusion. A research team did the work, submitted their findings to Nature Astronomy for peer review, and let the results speak for themselves. It is worth understanding exactly how Webb pulled this off, because the tools involved highlight just how far exoplanet science has come. MIRI, the mid-infrared instrument, detects longer wavelength infrared light, the kind best suited for measuring temperature from heat signatures alone. That is how the team first noticed the dayside was cooler than the bare rock model predicted. NIRCam, the near-infrared camera, operates at shorter infrared wavelengths and is better suited for identifying the spectral fingerprints left by specific gases, which is how the team identified the carbon monoxide and hydrogen signatures in the atmosphere. Using both instruments together allowed the research team to move from a general observation, this planet is cooler than it should be, to a specific testable conclusion. This planet has an active outgassing atmosphere, with a chemical signature directly tied to its interior. None of this was straightforward. 55 Cancri E's host star sits right at the edge of naked eye visibility, which sounds like it should make observation easier. It actually creates the opposite problem. A star that bright can overwhelm even Webb's extraordinarily sensitive instruments, effectively drowning out the comparatively tiny signal coming from the planet orbiting beside it. The lead researcher on this project has openly acknowledged that this data set turned out to be more challenging to interpret than almost any other observation Webb has produced, a remarkable admission for a telescope that has successfully imaged distant galaxies billions of light-years away and resolved the atmospheres of far fainter exoplanets across the cosmos. And yet here, a relatively nearby, well-studied lava planet orbiting a star visible to the naked eye, turned out to be one of the most difficult signals the team had ever worked to extract. That difficulty says everything about how hard it is to hear a planet whisper when its star is roaring directly beside it. It is also worth comparing 55 Cancri E to something a little closer to home. Jupiter's moon Io is the most volcanically active body anywhere in our solar system, driven by tidal heating, the constant gravitational squeezing and flexing from Jupiter's immense gravity as Io orbits, generating enough internal friction to power hundreds of active volcanoes across a moon smaller than our own. 55 Cancri E's volcanism operates through an entirely different mechanism. This is not a world being squeezed by a neighboring giant. It is a world being scorched directly by its own star, orbiting so close that stellar radiation alone keeps its entire dayside in a permanent state of molten flux. Comparing these two worlds gives researchers a rare opportunity. Two extraordinarily volcanic bodies driven by two completely different physical processes, each offering a natural experiment for understanding how volcanic activity shapes a world's atmosphere and surface over time. There is also a broader and more fundamental question sitting underneath all of this. What actually determines whether a rocky planet ends up habitable or ends up like 55 Cancri A permanent ocean of fire wrapped in a shifting, volcanically fed atmosphere? The boundary between planets that hold on to stable atmospheres and planets that lose everything to their stars' relentless heat and radiation is one of the most important questions in modern planetary science. Every lava world we study in detail adds another data point to that puzzle. One planet at a time, one impossible extreme at a time. This is also not the end of the story for 55 Cancri A. It is the beginning of a much deeper investigation. The research team has indicated this dataset warrants repeated observation over time, precisely because the atmosphere appears to be dynamic rather than static, changing between one eclipse and the next as outgassing ebbs and flows from the planet's molten interior. Future observations with Webb could eventually allow scientists to build something resembling a weather record for this world, tracking how its atmosphere shifts, thickens, or thins over months and years. The same way meteorologists track storm systems on Earth, applied to a planet where all weather is generated by volcanic gases erupting from a global ocean of lava rather than water evaporating from the sea. There is also renewed interest in comparing 55 Cancri A against the small but growing list of other known lava worlds to determine whether this same pattern, a hydrogen-rich atmosphere sustained by active outgassing, appears elsewhere, or whether 55 Cancri A is unique even within this already extreme category. Given how thoroughly this single planet has overturned 2 decades of assumptions, most researchers in this field expect more surprises, rather than fewer, as observation time increases. So here is where that leaves us. 41 light-years away, there is a planet that completes a full orbit every 17 hours. Its dayside is a permanent ocean of molten rock wrapped in an atmosphere that, according to every model built over the past 20 years, should not exist. An atmosphere actively fed by gases escaping from its own glowing interior, possibly generating clouds that form and dissolve within hours, rising above lava only to dissolve back into it. It is, by any reasonable measure, one of the strangest worlds we have ever managed to study in this kind of detail, and we only understand any of it because a 20-year-old theory was willing to be proven wrong. If discoveries like this make you want to look at the night sky a little differently, that is exactly why this channel exists. We will be back soon with the next mystery, the next frontier, the next place in the universe worth understanding just a little better than we did yesterday. Until then, stay curious, and I will see you in the next one.